Okay, in this little video demonstration, what we're going to do is we're going to take a look at Henry's law, which Henry's law relates to the solubility of gases dependent on pressure. Okay, so in our notes, we've already talked about that relationship, but now we want to see it kind of in action. So to do that, I have a couple of things for us here. The first thing I have is I have two different solutions. This first solution right here has all solid solutes in it. It's actually just kind of a Kool-Aid solution, non-carbonated. This solution here we have is a carbonated beverage, happens to be bubbly sparkling water. I am not advertising for this. I personally don't even like this. My wife does, but I don't. So we're going to take these two solutions and we're going to put them into a vacuum chamber and take a look at how they respond to a change in pressure. Okay? So the first one is our Kool-Aid, which is, again, reminder that it is only solid solutes in here. This is non-carbonated. So essentially there are no gaseous solutes for us to worry about inside of here. Okay? And we'll close out the valve and then we'll turn the vacuum on and we will decrease pressure. And lo and behold, we have an amazing result of pretty much nothing. Okay, we don't see any solid coming out from the bottom. We don't see any bubbling. There's no precipitation of particles. There's no sugar sitting on the bottom. It pretty much has no bearing on this solubility, which should align with what we know about the solubility and how pressure affects solids or liquid solutes. If I bring my chamber back up to normal atmospheric pressure, remove the bell jar. This is called a bell jar, by the way. And then we're going to repeat that process. But now instead I'm going to use a carbonated beverage. And we use a carbonated beverage because carbonated beverages contain dissolved carbon dioxide in its gas form. So this would be an example where we have a lot more dissolved gases in solution. Okay, seal that up really good. Close my valve again, and then we will again see what happens here. And very quickly, we see a lot more fizzing, very violent fizzing actually. Better turn that off. And we see what's happening here. This is not boiling. So previously in our demonstrations, we saw the effect of boiling water at room temperature by decreasing the pressure. Now, in this case, I'm not putting enough vacuum in here to cause that boiling effect in here. All we're seeing is actually the extra carbon dioxide that was in solution here being driven off because we're decreasing the pressure. Okay, so once again, we see that happen very quickly. And we see how much carbonation or how much carbon dioxide is actually inside these soda kind of solutions or these carbonated beverages. Okay. From this, we can then go back to what that relationship should be. We know, okay, looking at that relationship graphically, if we increase the pressure, so if I go now and I bring the pressure back, you'll watch, and almost instantly, as soon as I put the pressure back, the bubbling stops. Okay? Because as I brought the pressure back in, we brought pressure up. As pressure went up, the solubility of the carbon dioxide gas that was in that solution now increased. So what was there stayed. When I turned the vacuum pump on, we were drawing the gases out, creating vacuum or decreasing the pressure. By decreasing pressure above that solution, now the solubility of the gas inside that solution decreased, and as a result, the bubbling that happened. Okay, so we see that relationship that, of course, that we've already talked about in our notes. Okay, so this is just kind of an example of how we can look at the relationship between gases as solutes in comparison to how we see no real effect on change in pressure for our solid solutes.